Good afternoon, and thank you for this opportunity to present and be part of this panel. I will look at one of the publicly available databases to drive this discussion today. Our general practice is to rely on monitoring data, which is basically snippets of information, both spatially and temporally. We do not have enough number of stations in most of our cities to build a story just on that database. Using CPCB's own thumb rules, we estimated that we need at least 4,000 stations across India. As of last month, there are 310 continuous monitoring stations operational across all the states. Even the surveys and tests that we conduct to understand emissions are spread across very temporally. For example, a pool of emission factors were built for vehicles that was last conducted in 2010 for the CPCB's six city study. And there was one more round in a couple of years ago. So, altogether, snippets of data from different aspects of air quality. On the other side, we have the modeling world combining a large pool of data from multiple resources, helping us build patterns in emissions, pollution, and activity data, all in the hope of plugging the gaps in the monitoring data. But this is not an easy step. Actually, nothing is that easy. Here we illustrated major components of the modeling exercise. All of them are data intensive and computationally challenging and require substantial personal training to move forward. Emissions modeling, both aggregate emissions and spatial temporal allocations, need a lot of data. Meteorological modeling, easier than the others, but computationally intensive. We can use some feeds directly available from Indian Meteorological Department, but if we want some very local work, let's say at urban scale, 1 kilometer resolution, then we must run the models like WRF ourselves. Chemical transport modeling, depending on the requirements, the intensity of these models change. And finally, there are two major steps: validation, which is dependent on the monitoring data, and dissemination for public awareness and policy dialogue, which requires a completely different set of teams to take the message forward. While we are building our own made in India systems, there are several global systems in place combining emissions, meteorology, physics, chemistry, any monitoring data available, and the satellite retrievals to build a story on how pollution has evolved in the past 20 plus years. So, here are some examples. UCAR and MERA2 systems are based in the US, ECMWF is based in the EU. SAS is the reanalysis database built on NASA's MODIS satellite database by Dr. Sagnik Day at IIT Delhi. And the fifth set is from Washington University, St. Louis. This is Randall Martin's team. This team has worked with Dr. Chandra Venkataraman, who is also on this panel, 5 years ago on GBD Maps India program. So this new iteration is an update on that and also presenting model source apportionment data for the whole globe. And at the same time has updated the reanalysis data for the period of 1998 and 2020. So all these databases are available and open for use. So I will go over some of the insights from the data extracted for India. All the data extracted and summaries by state and district are available on our website for immediate use. Between 1998 and 2020, on average, pollution levels have doubled in India. This is also reflected in the calculated health impacts under the Global Burden of Disease studies, which also include a change in population size and health metrics. But generally, the big changes are being driven by the change in the pollution levels. On average, landlocked Indo-Gangetic plains moved from poor to very poor conditions. That's on India's AQI scales. And the central India moved from moderate to poor conditions. We can clearly see that the air pollution problem is not limited to the cities anymore. Looking at the same information overlapped with population and area, we halved the total population exposed to pollution levels that comply with India's national ambient standard, which is 40 micrograms per meter cube, and dramatically increased the population exposed to poor and severe levels of PM 2.5 levels, which is red and orange, red and maroon color bars, and the greens are basically everything under 40 micrograms per meter cube. Looking at the same percent population exposed, the biggest drop came on the lower concentration sides, which is 5 to 20 micrograms per meter cube. These used to be our background concentrations. What this means is that we have very small percentage of population exposed to pollution levels that comply with the new WHO guideline of 5 micrograms per meter cube. On the high side, we have more population exposed to concentrations more than 100 micrograms per meter cube. So these highs are traditionally confined to cities, but as the cities are expanding, these numbers are also expanding to more and covering more area. Now we are seeing the same trends in the rural areas, especially in the Indo-Gangetic Plain. Geographically, on average, we have 42% drop in the number of districts and a 27% drop in the number of states complying with India's national standard. Now, looking at what is contributing to the growing problem, 81% of the PM2.5 concentrations is sourced to fuels we burn in all the known sectors and resuspended dust. The message is simple. If we want to control pollution, we must find a way to reduce burning fuels or burn fuels more efficiently and with controls. On average, across India, residential cooking and heating is the largest contributor, followed by industries and power plants. Some snippets at the state level. Power generation dominates in central and the western states. Dust dominates in Gujarat and Rajasthan, which is expected because of the dry arid regions. While waste burning is a constant presence in all the urban and rural centers, the share is the highest in the northeastern states. The most talked about source, open biomass burning, on average contributes to 2% annually. But during the main burn season, that's October, November, especially in the Haryana, Punjab, and Delhi area, the shares are higher. At state level, the transport shares don't do justice to what we understand as their share in the cities monitored and analyzed air quality, where source apportionment studies are being conducted. Most of the source apportionment studies are being conducted. So we understand that the models come with a lot of assumptions. While these insights are very helpful, we must keep these limitations in mind. For example, global models run at a coarse spatial resolution. For example, the results I showed you today are from a model with 0.5 degree resolution, which is about 50 kilometers, which cannot capture the core urban activities at the resolution that we really want. The satellite retrievals used are also just passes over India, a snapshot, and not geostationary with longer timestamps for a given day. And we do not have a wide network of monitoring stations to feed these models enough to validate and calibrate some of these regressions that go into these big data global models. Despite these limitations, these models are helpful and should be used as guidance for the time being. There is no second guessing that we must expand the monitoring network, not only in the cities, but also rural areas where similar growing trends are vividly visible. We need more local level efforts to strengthen our understanding. This includes both bottom-up emissions and top-down source apportionment studies, especially the latter one, which should be expanded to rural areas as well. So under the current NCAP program, all these works are happening only in the cities which are listed as non-compliant. I'll stop here with these open questions for the panel, and I'm happy to be part of this. Thank you.